All right. Good morning. Sanbonani, Molweni, Dumelang, Goeiemorgen. So I've hit record now. So we basically going to start the lecture. And yeah, so let's just get through this problem. I like this problem for God knows why. It's one of my favorite problems. But I'll copy the images and then yeah. So we're going to do two things for this problem, right? And it's analogous to, of course, where we left off on the parallel load. Where we're going to have a so-called mechanical load or loading induced in the materials. Then what we're going to do, we're going to increase the temperature, right? That's the plan of this particular example. And obviously, when we increase the temperature, we're going to have resultant stresses due to the direct counterpart, the mechanical counterpart, as we're going to call, or I call it, and then also the temperature loading counterpart. Okay. So let me just copy that on the whiteboard, and we can just begin. So this is the actual example in your what is this? Your textbook. Discovered in the first chapter, and then I'll just wanna get this part of here just for explanation's sake as well. And I'm not sure this was touched on by I don't know. I think I was still in lecture at the time. I've got some of my thermos. Yeah, I'm not sure if I did, but obviously then I was aware I'll probably cover it over here. Okay. Nevertheless. So anyway, just explain the problem. So like I said, this is, we're gonna call this part A now. And of course it'll be part B. So this is due to, yeah, anyway. So let's just quickly talk through it. A steel bolt, several bolt, 50 millimeter diameter is inserted into a copper tube, right? We can have two images, so I'm sure you can picture that. And it has its own respective dimensions of 32 millimeters and a 26 millimeter external and internal diameter. It has a length of 200 millimeters with rigid washers on both ends, right? So we can see those washers there. The nut is adjusted to prevent any end play, right? Determines distance in both materials, either screw thread has a pitch of 2 mil, and the nut is tightened 1/8 of tightened by 1/8 of a turn, right? So obviously that's a full circle. I think I'm not sure exactly what an 1/8 is. 1/8. Yeah, 0.25, whatever percent that is. So it's turned a specific, let's say, arguably a fraction, some kind of fraction of the of that circle. So once this happens, and this is what they're essentially showing on the sketches over here, that what you end up finding is that you obviously deem this as a parallel problem. It looks like, oh no, it's a parallel problem, but no, it's not. So it's a very peculiar problem, and that's why one must really look at really think about certain problems and just not apply laws to it. But the idea here, it's on page 34, and as you tighten the nut, and they talk about this actual wound of the nut. So obviously, as you tighten the nut, what will happen to the what is this? The tube. The tube will be compressed, whereas the actual bolt inside will start to extend, and that's the whole purpose of this. And of course, so we get compressive load in the tube, and the tensile load, of course, is telling our sensors. And then what's also important, the force is of the same magnitude. So yeah, so the two equations you're going to be using, your static and compatibility one is just going to be, I would say, force steel equals force copper, excuse me, and also another thing, and also for our compatibility equation or the length is that in this case the lengths are not, we have to add each length, right? And this will be equal to the number of turns. So just look at this number of turns. Very important problem, guys. times pitch. All right. Okay, so that's that. Yeah. So basically, the pitch is obviously if you have your bolt, that's the distance between the two threads. That's what the pitch is. Okay. And it's a fairly simple thing to actually to sort out here. So what we do is the standard setup we normally do. If your forces are equal, then therefore we can say the stress of the steel bolt, area of the steel bolt, and then it's equal to the brass. I'm just using copper as my way of sorting my things. We need this ratio, so we have steel bolt diameter 0.015 squared. The reason why I'm not including the power 4, obviously, because they're going to divide out.
Sorry,
and then I have
what?
Oh, flip, man! I'm not sharing that. Yeah, sorry, guys. Yeah, I'm already like deep in. Yeah, so I was writing, guys. I thought I've shared it. Okay, yeah. So I basically started solving the problem. And yeah, I am just taking the ratios between the two forces so that obviously I can substitute it in the compatibility equation. Okay, then obviously we have the copper now, so that's 0.026 squared minus 0. Outer minus inner. And then yeah, we should be able to get a ratio. So I'm hoping someone can just quickly give me that ratio.
116 over 75.
1.16?
Yeah, 116 over 75.
116 over 75, okay. That's quite strange. No, let me just see what the value is. 1.54, okay, that's fine. Can work with that. Obviously, from this, we substitute into here. In this case, so we expand this, guys, so that will be stress this will be the steel, this will be the bolt. Go to the tube. And then again, talking to this, it's just going to be, it's normally always given 1/8 of a turn and times 2 more. All right, so that'll give us, oh sorry, this should be 2 times 10 to the negative 3. So always keep it in SI units. If you go that on the other side, you should get 1/8 times, so it's 250 times 10 to the power negative 6. Obviously, there's a very, very small change of length. From here, you guys can either, so stress of steel, the length, I think the length was exactly the same of 200. So 0.2 steel's modulus of elasticity is 200 gigapascals, and then you've got copper, same length, and then you've got your, I think copper, let me check copper's 100, yeah, should be 100. Okay, so obviously you guys can actually just sort this out. You know, I would have just done this, copper 116 divided by 75 equals 0, my first equation, and my second equation, and I just have a matrix, right? Obviously you guys can do what you want to do. You can substitute that into there, and obviously just sort it out. So can we get these values? And remember, values and senses. You get a mark for the value and sense. If you don't include the sense, you lose a mark. Always remember that. So you get a mark for the magnitude and the sense. Magnitude and the sense. Just be aware of that. No sense, no mark. I've said it here. Okay, I'm just waiting on these values.
Okay, well, stress of the copper is 70.4887 megapascals compressive.
Okay, 70.48 you said, right?
Yeah, I got 4887.
Okay, 488, that's fine.
Okay, compressive.
Yep.
And stress of the steel is 109.022 megapascals tensile.
Okay, 022, yeah. Okay, MPa. Important. These senses are so important, guys. Important. Right. once this is done, we've solved part A, right? Then assuming this arrangement, I'm not sure exactly where this could possibly be. Maybe a heat exchanger. No, I think the temperature I'm using is a bit too lenient for that. So what we're going to do now, we're going to end up, I'm just copying the actual question here. So this is not in the textbook. I think there is almost similar to this in the textbook, but yeah. So, just moving along over here. So I'm saying assuming that part A has happened at 25 degrees, and this is for you guys now. I want to see you guys have some. And what happens is now, I'm asking find the resultant stresses induced in the assembly is raised to 50 degrees. So we've got an increase of 50 degrees, right? So I'm not sure exactly what's happening, but some of the temperature has increased. Could have been arguably in the engine room or something, right? Let's say we've reached 50 degrees for whatever reason. So obviously we have our expansions, and yeah. So we can apply exactly the same setup, but now remember we're gonna have. So I think because it's a similar thing, we can have similar ratios. The force is going to be equal, so force of steel equals force of copper. So we essentially really end up with the same. What's the stress of steel is equal to, what is this? Stress of copper 116 over 75. And then now we need to use our formula. I don't know which arrangement is this. So you guys can tell me which arrangement is that.
Parallel.
Parallel. Beautiful, beautiful, beautiful. It's parallel. See, I could have given this in the test, and then everyone's going to start suffering like, oh no, so why? And then obviously, what we can do here is a stress of steel over that plus stress of copper over that. The reason why I'm doing this, the length is probably the same. Obviously, you guys have played around with the formulas, and you know you can kind of repeat it with just this. Yep.
I've got a quick question for you on that.
Go for it.
For that length, I don't know if I'm going a bit too in depth. I'm off the topic, but I don't think you can say that the lengths are the same. No, it's not about the washes because no, because you're saying now, so we've said part B, so part A has already happened. Okay, so length A and length B won't be the same because you've already increased the length slightly of A and decreased of B. Not so?
I see. You're actually correct because I'm assuming that this happened afterwards. Yeah. Because obviously the length will change. Yeah. No, I'm with you because if we did this before, the lengths increase and the lengths decrease. So obviously we have new lengths and new. I'm with you, but no, it's fine. We can assume the same length. It's okay. I should have stated that. So that's a big assumption I should have made. Yeah.
Yeah, I worked it out. The answer change is minimal between them, but I just thought, I don't know if you're going to allocate extra marks for including that different length.
No, I should have. I would have. Yeah, assume length remained the same. No, I was aware it's probably going to be small. Assume length remains the same, but it must be stated in the question. Otherwise, you're going to spend, But you, I'm laughing that you actually thought about that, and it's actually proper. Yeah. Okay. Cool. Should we say this is happening concurrently? Or at the same time, and maybe we can make the question a bit better. Now, but that's proper, man. Okay. So let's work that out. But yeah, no, that's proper, because obviously the lengths are going to change, and we can obviously work out the change in lengths here. So if we just look at that, don't have to do this, but obviously the new length. But so what's the length of steel? So that'd be 0.2 plus that basically. You can see how small it is, just for the ease of. No, it's a great question. So you can just quickly work that out. Now, but you can the length will be. I'm assuming the lengths are the same. Yeah. So yeah. Yeah, it's 0.200109. So yeah, it's fairly close. But yeah, we can keep the same length of 200. So therefore we can just cancel that out. Okay, so let's let's get our new stresses now. Maybe someone besides Mr. Engelbrecht could possibly solve this. This must be. Casper, have you managed to solve this? So stress of steel, I'm just going to set it up for you guys. 200. Copper, 100. We've got 20 and minus 12. And of course, we went from 50 to 25 to 50. So, yeah, it's even more interesting when the temperature decreases. So, yeah, you'll see. Okay, so yeah, we need new stresses now. So I'll just wait on you guys to sort this out. Yes, go for it.
Because it says assume it happened at 20 degrees Celsius for part A. Part B, it's been raised 250 degrees. So is the change? Do we use the change as 25, or do we use the actual temperature?
My bad. Yeah, it's 25. It's 25. I thought I did that.
So, no, so that T is delta T then, right?
Yes, that's correct.
Okay, thank you.
Excuse me for that. Okay, so Jason, what is that? Which answer is this? Is this your resultant stuff or your actual stresses? That looks like resultant values to me. What is my actual? What is this? What am I looking for here? What is your stress due to temperature? Yes, Sasha.
Yeah, it's stress of the copper due to temperature, 11.25 megapascals compressive.
Okay, 11.25. Yep, steel.
And then 17.401 tensile. But I mean, obviously, I just used the new length, so the decimal places are going to be slightly off.
Yeah, no, it's okay. Concept is there. Concept is all there. Yeah, okay, yeah, you got it. Okay, guys, so, and this is, a lot of students make this mistakes, and that's why I've played around. So your resultant for steel and your resultant, or maybe I should call it denoted like this. What is S here, and what is this? Copper. There's another question. Oh, Alex.
Yeah, so if you don't include the temperature coefficients in the question, must we just assume what they would be for that particular material?
Yeah, normally I always give it. It's very seldom I don't give it to you. But if you assume it, fantastic, yeah. But I will give
Okay, good. Now, the reason why I'm asking, I think that the test you posted for strengths, I don't think it has the coefficients in the question, so I'm not sure if you have to assume or not use them at all.
Oh, I wonder. I think that is missing, and I mentioned to them afterwards what the values were. But it's a standard value. It's probably 18 and 12 depending on the materials. But between our break, I'll sort it out. Sorry, I didn't actually know that. I've actually updated the test and I thought it was done, but okay, it's cool. Yeah. No. Guys, I don't do tricks. I'm telling you now. I'll tell you there's like what kind of tricks I expect. This is the tricks I expect. And the reason why is that, okay, as you can see here, that's tensile, so that's 109 plus 17 point. I'm not going the decimals really. 17.4, 109.02. You get that resultant. They're both positive, which is important, and this is going to be 70.48 or negative rather 488, whatever, minus is at 11.25. You get that guy, and that Mr. minus basically sorted out, and that was 126.466, 126.47, 126.47, and the other one was 81.77. Yeah, beautiful. Don't forget your sensors, which is important. All right. Yeah, there's a truckload of marks, shipload of marks here. It's 1, 2, 3, 4, probably one mark for that. Up there. 1, 2, 1, 2, 1, 2, 3, 4, 5, 6, 7, 12, 13, 14. Yeah, easily 14 marks. Okay. So what we do now, we have a part C. We thought it was over. It's not over yet, guys. Not over yet. So I'm gonna. I think I should actually just. Yeah. Let me hit back to the slides. And this is it. So we've got a new part here, and this is now the skull spice, as I would call it. So now we always talk about things remaining have structural integrity. They last, they're stable, they never break. But now I would like to see something, right? Part C. So assuming the bolt spec is ASTM 307, that's a real bolt spec, by the way, and the tube is C145, 14,500 soft. I'm not probably pronouncing it right. If the assembly is raised to 125 degrees, Mr. Kessler, he was asking me such questions. Which elements will fail or be structurally sound? So what you're going to use for the bolt is this 155. That's going to be the allowable shear stress, right? You know, we always talk about the allowable value. That's the one. I'm not being fancy with any factor of safeties. And if you look at your C copper, your soft one, we're talking about, we're going to use its UTS, right? So normally you want to use its yield, but okay, we're just going to be fancy and we're going to use the UTS here. So 221. Okay, so that's your allowables. So now, Mr. Doyle, somehow, I don't know exactly what happened. There's probably an explosion happening in the engine room. And somehow this arrangement, well, obviously the explosion, obviously the temperature probably should have shot up. It transit, let's say after the fire and after the explosion, kind of settles to 125 degrees. Can you guys please tell me which one would fail? Is the question clear to everyone? Sasha?
Another stupid question. When I did this yesterday, I did it 2 ways as well, because I wasn't sure if you give it, like, say you said it, what's it, C145 soft, they give you the modulus of elasticity. Would you want to then rework the stress based on that new modulus of elasticity, or then do you just carry on assuming that you're using the previous modulus of elasticity?
No, so remember what I'm giving you here now, Dr. Engelbrecht, is that you have now the material. I'm characterizing material as an allowable. What I'm saying, it has a limiting factor of how much stress it can handle now. I think we get it, 155. So it's the same analysis. Nothing has changed, but all I'm doing is increasing the temperature up to 125 degrees. Are you with me? And therefore, obviously, I'm assuming we're both using the mechanical loading part plus the new. I'm kind of continuing the question. So I'm increasing it up to 125, and let's see what's going to happen. What are the new resultant stresses? And based on the new resultant stresses, has it compare that to the allowable? What has happened? What is gonna be structurally sound, so to say, and what's gonna fail? I think, is the question clear?
Yeah. What I was asking is, because if you look at that bottom table you've given there, they actually give you the modulus of elasticity. The material.
Oh no, the previous.
So
the previous one.
Would you have to rework? Okay, that's all. Just
No, the only reason why obviously this table is from another book and it's more comprehensive, but it's the same modulus of elasticity. It's not changed. It's just that I'm just showing you the table with these values. That's all. But you always think the right words. It's good to be critical as an engineer. The same properties, man. Just looks. I could have just removed the tables and put those values in, not confuse you, but yeah. All right. Okay. Batana, good morning. Good to see you here. Okay, so grandson, I hope you understand the question. Yeah, special last question for temperature. I just made sure I wanted to do this. Yes, Alex.
So can you just go to part B quickly? I'm just trying to check the stresses there. I don't get the same stresses.
Oh, should I? Okay, let me just. Yeah, there we go.
120.
It's fault in tube, right?
Yeah. Okay.
Okay, I'll just move back to the question. See, guys, what I can also do with a question like this is ask you which bolt will you select. Are you guys there? So I can ask you, select a bolt based on your answers. Which bolt would you use? Now, I hope everyone got that. That's the way I kind of test you, you know, it's not plug and play. Yes, Mr. Motaso.
Yes. Yes, sir. I found the new stresses. For copper, I got 45.
Okay, let me write it down. Let me just switch this here. Okay, I'm with you. For copper, what's it? 45. Hey, the guy just disappeared on me now.
It's not the resultant. That's just for the new temperature.
Yeah. Okay. Just I'll write it here. It's fine. So go for it.
45,11 megapascal.
Yeah, and therefore the resultant is what?
I think that's 70 times or minus.
Mine. Yeah.
45,11 minus 70, something.
It's not minus.
It's not minus?
No, because it's two compressive stresses. Your original stress was compressive, and this is compressive as well. So you add them. So it's
it's minus
yeah,
minus.
Yeah, that's correct. Okay, what is the resultant? 115.60. There's a minus on fire there. Yeah. And then 115.60 megapascals compressive. It's all the same.
Yeah.
What's the new steel one? Let me just have a look.
74,75 plus 109.
So 74,75.
Yeah, it's gonna be 183.
Point what? No points.
There's points, but I didn't.
Make sure Mr. Minus got there. I'm assuming he has 178, eh? It's different answer.
I got 178. I got 178.
Yes, 178. Okay, yeah, it's good enough. Okay. So looking at allowable stresses for the bolt and for the you know what I'm talking about here. Let's just revert back to our previous thing. We've got 115. You've got that small copper. Copper was what? 221. This is very sus, obviously, because we're using the UTS, so it's not fairly comparable. The concept still holds here. Obviously, you would compare it to probably the yield. Yeah, but I'm just using this for the concept. And looking at the values, this is less. Therefore, this will be okay. Copper will be fine. It's less than 221. However, our bolt's going to fail in right? It's going to break. It's a horrible looking bolt. Yeah. By the way, guys, you know, it's one of the things I'm interested in is failure analysis, and there's a whole lot of literature on how things fail and how they look. Yeah, there we go. Beautiful. Okay, and you see, based on a question like this.
Can I ask you a quick question?
Yeah. Yes, go for it.
You've passed the limit of proportionality already. You've gone over the yield strength. So hasn't that failed?
You're doing it for the copper tube.
Yeah, because they're saying that your yield strength is at 69. So after yield strength, you don't have any elastication. It won't go back to normal. So
yeah, exactly. Yeah, that's what I said. I was using this value, man, as like a concept. I could have used, obviously, it should have been 69. I didn't mention that just now. So I just use the UTS in this case. Yeah. The point is to compare values and see if it's one is greater than the other one as a pass or fail. That's the point, you know. obviously, steel is much more, and it's a steel bot, by the way. It's much more strong than a a soft copper rod. You know, I could have chosen a better material like C7200 beryllium copper at 138. You know, I could have just chosen that one to make things more, of course, more realistic. So yeah, so, and then based on these answers, I might ask you for next extra 2 marks. Which bolt would you choose based on the table over here? And then, you know, you can maybe just choose a bolt which is stronger. Yeah. Okay, I think I just want to touch on those 2 parts. You know, I don't do part D and E, but yeah. So how do you guys find this problem? Well, it was challenging. Do you enjoy it? Yeah,
nice,
go for it.
But I just had to make a lot of assumptions though.
Yeah. Yes, it's a theoretical problem, Prof. Engelbrecht. Just relax, it's okay. Yeah, yes, Alex, just go for it.
Yeah, the only question I have is, like, I think I just need to go through it. I wasn't really able to, match your Formula One speed there, but anyway.
Sorry.
The only question I have is that in part B, it asks that the temperature is raised from 25 degrees to 50 degrees. So your change in temperature is 25 degrees, correct?
That is correct.
So now my question is, if the temperature was decreased from 25 degrees to, let's say, like -2 degrees, what will your change in temperature be? Is it 27 degrees, or what would that change in temperature would you use?
So you said if you went from 25 to -2?
Yes.
It would be 27 degrees.
So you would put 27 degrees there, for your change in temperature.
Yeah, but we have to be aware that now it's contracting now, and that makes it more fun.
Okay.
Yeah. So not supposed to be. That's what we're doing. It's minus, plus. Yeah. That must change the temperature. Yeah. Should be, if I'm interpreting the question right. You could actually do that and see. Maybe I'll try to create a question similar to this.
Yeah, the reason why I asked is that the test you posted, the temperature decreased from 35 degrees to -2, so I wasn't too sure exactly what the change in temperature was. Okay.
Yeah. Oh, but yeah, you asked for the memo. The memo's at the end of the test, is it not? Have you had a look?
I don't think so. I think it just says end of test, but I'll double check. So I'm 100% sure.
Maybe I posted the wrong one. So it does have. Yeah. Anyway, okay. Let's start a new chapter, guys. So, okay, guys. We can start on strain energy now. So let me just quickly close that off. Just strains are not too bad, guys. You shouldn't worry too much. It's gonna get fun at the second half. Yeah. All right, so let's just quickly start on the next. Actually, what I should do now, I'm gonna stop recording there and just restart again. So I'll just